Welcome to episode 32 of Roid Rage. Can you hear me now? Per usual, we have our guest here, Matt, our CEO. But we have our special guest here today as well, Christopher, who's our software engineer. You have to talk.
Hey, I'm Chris.
There you go. And Max, who's our RF engineer.
What's up?
and notably, no Chap.
And yeah, so Chap's not here, so you get me, which is clearly
a downgrade.
Huge mistake. All right, so clearly deep space comms are fundamentally messy. Yeah. What can I say? We've had a lot of episodes about that, so I don't really want to get into all that. So what I do want to get into is exactly, Christopher, what was your role on Odin?
Well,
This is like my favorite story.
oh, sure. So I joined 2 weeks before Odin launch. I did so I'm on the flight software team, so we mainly write software to control the different pieces of hardware on the spacecraft, send telemetry down, accept commands. And so I reviewed some just unrelated pieces of code, like how we're going to do software updates quicker and how we're going to do downlinks and chunks. But the most memorable thing is I think it was 5 days before launch.
So you had been here a total of 5 days.
Yeah, I'd been here 5 days, and my manager, Armand, sends me a text and it's like, do you have a valid passport?
Never a good sign.
And I was like, yeah, I have a valid passport. He's like, well, we need someone to go to Portugal to help set up a ground station. And, I don't know, I'm not on the, I hadn't really been working a lot with the ground team. I had met Michael and Bobby, who were the ground team at the time, but I hadn't, really interfaced with it beyond there was something we were debugging or looking at. So I didn't really know anything about it. He was like, yeah, we just need you to essentially bring this hardware, plug it in, help set up connection back
to Portugal, by the way.
To
Portugal, which we all, to be clear, when we told you that, we thought it literally was going to Portugal.
Well, yeah, and so Robin sent me a pin on Google Maps, and I thought it was broken because it was in the middle of the Atlantic Ocean. I was like, oh, this link is broken. And then I zoomed in a bunch, and there's this very small island in the middle of the Pacific called Santa Maria. 5,000 people live there, and that was where the dish was that we had to set up. So I took 4 flights.
Which, by the way, is technically Portugal, I think. That's how we got
so
it wrong.
No,
So
it's
I learned about it while I was there. So yeah, it's like an autonomous region in Portugal. So they have their own elections and stuff, but they're still connected to Portugal. They still get defense from Portugal. Also,
So it's like our version of Puerto Rico?
Huh?
Is it like our Puerto Rico?
I'm not as well versed in the politics, and if someone listening knows more about Azores, then
Oh, you don't know how this show works. We talk about stuff we don't know about all the
but
time.
I'm just saying, that was my understanding. That's what the people there told me. Anyway, so we go there, and I bring the things I would bring were the digitizer, which will take the waveform and turn it into digital data, and then the radio, which will take that data and allow us to get a frame and then put it through our ground software. And we also they already had their switches and different pieces of network equipment so that we could set up a VPN, a virtual private network, where we can encrypt everything between us and that ground station. And it's a huge dish. It was very cool to be there. And unfortunately, we got it set up and we had a test and we were transmitting. And as we'll talk about later, it's very hard sometimes to do uplink. There's just not a lot of stations that have the power we needed, especially for Odin. And so it was great that we had Santa Maria and we got uplink working, but then the power amplifier that kind of takes the signal and makes it strong enough that it can reach the spacecraft broke right before the launch. And
Is that your fault?
No, that was so. That's a great question. No, that's just always
Wait
that's
a
like
minute.
Why is that a good question, Chris? It's actually a terrible Did you fuck it up?
No. So they have their power amplifier as part of their ground station, and so they do other missions. I'm not sure exactly what I'm allowed to talk about with this ground station, but they do other missions.
Chris. First off, legally, you're allowed to talk about everything.
Well, this is
That's not
an
true,
ESA,
Matt.
this is an ESA thing rather than an AstroForge thing.
I don't think anybody in Europe's going to sue us.
Okay.
Well, there's nobody. We don't have any listeners.
We don't have
in Europe.
anybody that listens to us.
Cool.
So period.
Well,
But
Especially-
nonetheless, no.
I won't say. I'll just say it. The European Space Agency. This particular ground station supports missions. I think I can say that it's. If people are familiar with the Ariane 5, that second stage gets downlinked there. And I suppose uplink. I don't know if they do uplink to it, but they have a lot of missions they support, and all of those missions could also not get uplink. So they were very stressed by
That is
power
why
amplifier, not
they
just us.
always have a backup power amplifier at the site, right?
No, and we almost went to Italy to get like a backup power amplifier, and I had like this guy who normally does tours in another island ready to take me like back in time, but then the power amplifier in Italy wasn't ready in time.
So we worked with Peter on this when it broke. By the way, they told us at the beginning, like, oh, of course we have backup components if anything goes wrong. And then they don't have it. They told us later that they, I believe, put it, what broke was the backup from a couple weeks ago. Who knows if that's true or not.
Well, so what broke was the backup from like several months prior. There had been another similar issue.
So we looked at
I'm gonna move on, Matt, because like Max has fallen asleep.
I'm taking notes. I'm learning.
Max is gonna have to go next time.
I'm always ready to learn. And listen, most importantly.
Yeah. No, now I need you to talk though, because
Okay.
like
Yeah.
we kind of jumped ahead because like honestly, that's like a really interesting story. Having to take like 4 flights with a digital box and like
1 week into the company.
Huh?
just another weekend.
Did you almost quit when you were on in the Azores? Were you like,
No,
fuck
to be
these
honest
guys?
with you, I thought it was
was
kind of
that close
cool.
about
I was
moving
like,
on.
this is actually pretty sick. Like, I felt like part of the team. And
Well, you were
everything,
part of the team.
Yeah. So it actually was, not so bad.
All right. So other than travel and frequent flyer miles and those kinds of issues, going to small islands that you can barely find on Google Maps, Max, what makes deep space communication hard exactly? I mean, compared to like LEO or GEO.
There's so many things that can break. It is a nightmare. And part of that nightmare is that the path loss from the Earth to the ground, that's the amount that your signal gets attenuated or reduced on the way up to space, is on like off the top of my head at least 1 billion times more than what you'd see on the GEO or LEO area, at least out to the distances that we're planning. So in order to build a resilient system to go out this far, we have to make a lot of different considerations from what your garden variety LEO or even GEO mission would have to do.
Well, I mean, let's talk about some of them. I mean, like power, pointing.
So our power amplifiers on the spacecraft and on the ground are pretty intense stuff.
Do we have backups?
We do have backups.
Oh, okay. Just checking because
We've
case
got
they burn
backups
up?
for the backups.
Yeah.
We've got 2 receive chains and 2 transmit chains. Each of those individually have 2 separate paths that our signal could take. So we would need 3 failures on either our transmit or receive side in order to knock everything out.
Why? We're supposed to be a single fault tolerant spacecraft, so why do we have 3 fault tolerance on the RF system?
I did not design this system, but
'Cause
I
Robin-
can tell you that
Robin started
sounds like a
working here.
redesign. Sounds like a redesign.
Well,
there was
it's
some
still
scary stuff going on in that first mission, or mission 2, I suppose, first deep space mission, that I think drove a lot of these decisions.
Yeah, we only have 2 radios still. Like, so if we're only, we can only lose 2 radios.
Sorry, we can only lose 1 radio.
Yeah, if we lose 2 radios, we don't have no radios.
Maybe we
What
should
I-
talk
what
about
I
how
mean is we can
redundancy
al-
works.
Well,
a
sorry,
little
what I'm
more.
saying is before mission fails if we lose 2 radios. Mission's degraded if we lose 1. So yeah, like you're saying, we're 1 fault tolerant.
I think it's an important thing to note, though, as we talk about this, we always kind of come in here on the design side. Every engineer wants to make sure their system doesn't fail. It's not the fucking point. The point is that our spacecraft is successful, right? And that comes down to mass, cost. There has to be a lot of variables that have to align there. So on the spacecraft side, can you walk us through the input and output of that RF system at just a high level?
Yeah, absolutely. So as the signal is coming, the real input to this system is at the ground station. So I guess I'm going to do kind of a link budget walkthrough here. So your ground station is going to modulate your signal. So that's just putting it into a radio frequency wave to be sent up. And one of those first inputs is the power on your ground station. So that's got to be pretty damn high. That's got to be, I think some of our stations are around 80 dB watts transmit power. That's 10 to the 8 watts, I believe. That sounds really high, but that may be correct.
I have no idea what any of those numbers mean.
I
What
might
can
be
you
talking out of my
what
ass
can you
here.
compare that to?
How
How much is a dB watt?
It depends on how many dB watts you have. I won't talk in dBs anymore because I think it's pretty confusing for everybody. But the reason we use dBs in RF is because for long distances, say, I'm going to use it one more time, we have about a 250 dB path loss. dBs in general are logarithmic units, so they really represent a multiplication. So if we subtract 250 dBs from our link, that's equivalent to reducing the power by on the order of 1 trillion, I believe.
That's a big number.
It's a huge number. It might be more than that.
It feels like we got to do some real-time ChatGPT checkup.
Yeah,
on that
Ray,
now.
can you ChatGPT for us and can we get a fact check over here? Let's fact check. Max, we do fact checking on this podcast.
Yeah, we're doing.
That's all
FYI.
Can we get a fact check?
I'd
Fact
rather be
check on
fact-checked
guest
and
number
put it in
2.
my notes and then be ready.
do the
How
fact check
much
with
is a loss of
ChatGPT.
250 dB in
in
terms
linear
of
units.
in linear
Power,
units? Yeah, there we
yeah.
go.
You were struggling there.
I was
Matt.
like in terms of
No,
what? Like
that's-
I don't know
yeah, no.
English, but that's not really.
I mean, another. So just this is my. I am not an RF person. I just want to say, but one of the way I think about some of these things is like, I was actually looking this up before, and you should fact check me, but like sound is another thing that you measure with decibels. I think that's the classic one most people are familiar with, and like the difference between like a very light whisper and like an incredibly loud bang being right next to a firework. I think was only like 80 dB or something like that. So if you imagine like the difference in power between a sound you can barely hear and an incredibly loud sound, that's just in a different domain of.
We should have all been scientists in the 1800s because I believe decibels comes from James Bell, the inventor of the telephone,
Well, yeah,
and his unit of how to do it. I don't know why it's why it's 10 of
because
them.
it's base 10.
Yeah,
Okay, never mind.
What's
I'm
the
not gonna explain
logarithmic
it.
system? So it's not base 10. It's what the fuck? Regardless, I don't know why he got it
It's
off by
base
10.
Well, no, they're deci just because it's easier to work with. In the quantities that you'd see normally with the way the decibel or just
So he
the
was
bell is
wrong.
defined. Yeah, he
Ray,
kinda
are we
jumped
right
the
on this
gun a
fact
little
check or
bit.
not? This is a really slow fact check.
Well, what I can tell you,
What is it?
10 to the negative
Yeah, in
25.
linear units.
That's more than a trillion for
Yeah, that's-
folks at home.
Yeah, that's more than a trillion.
Yeah, that's a pretty big number. I don't actually
That's
know
like
what
bigger
the
than
name
the-
of that
that's
number
like
would be. That's
Bigger than the national debt in dollars.
I don't know if that's true. Okay, let's continue.
that can't be more
Really
than
big fucking number. What happens after that?
So we hit the antennas on the spacecraft. And you got to keep in mind that we do have pointing issues going from the ground to space and on the space side as well. So our ground station is trying to track the spacecraft, but it's not exactly on top of it. And the spacecraft is trying to track really the Earth at the distances we're at is what it's focused on. But even that, it's within a 1-2 degree error, which is
Well, that
also
sounds pretty good.
You'd think so, but our ground stations, these antennas are crazy tight beam widths. We would call the beam width the area where most of the power in the signal in physical space lives.
Like yelling in like a cone.
Exactly, yeah. You'd have a beam width in front of that cone that is much louder than to the sides. Remembering some of the numbers from our ground station database, I believe some of our antennas on the ground have beam widths of about 2 degrees before they fall off by half the power.
Wow.
So
That is not true.
that is absolutely true.
No, the India dish has a beam width of 0.15 degrees.
That's
or it's
insane.
3 dB. So that's why it's not true. It gets
Okay.
worse.
I'm pretty sure Max said some of.
Sure, some of them, but the ones we use are a little bit even harder.
No, we're not going to use that one.
It's regardless of what the number is, whether it's 1 degrees or 0.15 degrees, it is very small and it's very difficult to track. I wouldn't be surprised if it was 0.15 degrees, So all of that is to say that we incur some serious loss just by misaligning our ground station and our satellite.
So, but it's not just about power, right? What about bandwidth?
So we're limited by the FCC on our bandwidth. So while this signal is traveling through the atmosphere, through space, there are people listening on nearby bands, right? So I believe that without getting into too much detail, our planned uplink is inside of the JPL DSN restricted band.
That's true.
So we got to be super, super careful that we don't leak above our designated frequency band or below our designated frequency band, because then FCC's on our ass. And that's also why we can't transmit from the US, right?
Well, Max was just like, psh, smack you in the face. Why can't we transmit? This is the weird. I don't understand this. Why can't we transmit in the United States?
I'm not going to pretend. Was this a Robin question?
That's why I'm looking at Robin.
I think this is a Christopher question. I'm the host today. I don't have to answer a thing.
Well, I can tell you, I definitely don't know why.
Oh,
we
man.
can't transmit in the United States.
All right, fine. The host will answer the question. There is a rule in the United States to protect our ability to communicate with our deep space spacecraft that you're not allowed to transmit in the experimental deep space S-band frequency range, specifically so that we can hear our deep space spacecraft, like Voyager, that's, I don't know, bajillion miles away. I don't actually know how far Voyager is.
It's pretty damn far.
It's
I can
pretty
tell
damn
ya.
far.
Yeah, I think it's out of the solar system now.
Yeah, it's definitely out. I was trying to remember how many
It's-
light
it's-
days.
I believe it's either 8.2 billion miles away. I think it's 8 point. Ray, fact check Ray. How far away
This
is
is great.
Voyager?
Ray, we're going to get
Yeah,
Ray. in
I
all
really
of
like
these.
this. Ray's like,
I mean,
thought he was
Rachel
going to come here
never
and chill
helps
for
us
an
this
hour,
way,
and then
like-
he's like, fuck. He's got
Except-
ChatGPT open fact checking us. Like, wrong.
Except that, wait, Ray, don't you have another job to do?
He's probably trying to do it right now.
Thank you, Ray.
How far away is it?
168.46
And how many
What is that
light
in miles, Ray?
days is that?
Well, can
All right, we're going to move on.
15.7 billion miles.
I was off by 2. That's pretty good. I'm going to give myself credit for it.
All right, well, look,
So-
we're just going to move on. We're not going to talk about that anymore because clearly these are all big numbers and they're in dB and
Well,
AU
so
and
there
like they're
is
so
an-
big that we have to use other units.
There
right?
is an interesting thing from software for this that I don't know.
All right, hit it up.
about.
What do you got?
So like in Leo, I used to work on satellites in low Earth orbit and in like medium Earth orbit.
Boring.
Yeah. Well, I thought that was cool. But there's essentially like with those, one of the things you can do is you can get pretty good throughput. You can get up to like 100 megabits per second in some of these cases, and so you also have much better latency. So latency is actually I think an underappreciated thing where it's like. Even in geo, latency starts to get kind of bad. In Leo, latency can be as good as like your connection at home. And so there's protocols we can use. We can use the same protocols we use when you like open a web page if you want to transfer data between satellites in low Earth orbit, and it kind of works. If we try to do that here, we're going to be waiting a long time. Like we're going to send one message where we'll say, "Do you have anything to send us?" And then by the time we get a message back, knowing that we're clear to send, we've already wasted a lot of our opportunity when we could have been transmitting. So we have to do some things a little bit differently. We have to essentially send as soon as we know that we have a physical connection, we can start sending, and then essentially the ground needs to be in charge of knowing like, hey, do I have everything? So if we're downloading a file, we'll take a hash of the file. So it's like a code where if any of the data in the file changes, the code also changes. So if you can produce that code, then you have the right data. And so we'll send that down, and then we'll send down a bunch of chunks. And then if you're missing any chunks, you can go and re-request those chunks. And so it does complicate the software a little bit. You have to essentially transmit without knowing that the other person can hear you yet, and then they need to request what they've missed.
It is a little bit ridiculous. It's super cool, though. Our one-way time of light, that's how long it would take for a signal to get from Earth to the spacecraft at its maximum that we're building for. That's about 1 minute, 7 seconds. So on the way back, that's about 2 minutes, 20 seconds, more or less. So imagine trying to have a conversation with someone where you'll know that they received your message after 2 minutes, 20 seconds. And because of our pass window size, we'll only have a marginal amount of time to hold that conversation. We
So
might
it's
be
like
able
when
to
it's like when
get-
you slack Robin.
No, yeah, that's
It's a
just,
lot
you never get a
better than when
response.
you slack Robin.
I totally was going to say it's like having trying to have a conversation with your kids at dinner after school. Like, you ask a question and crickets,
It's nothing.
just
Yeah.
nothing. It's fine.
It is interesting though that every modern piece of software that we use in our modern internet or just communication protocols, it doesn't work. This is a
Yeah,
connection.
no, just totally time out. Be like, clearly you're disconnected.
Right, and it would reset, and so all of those things either have to be rewritten or used by us, which is a pain in the ass because those have been optimized over the last 2 decades to make them extremely proficient, really good, and robust. And we don't have any of that. We're on 1970s internet is probably the best way to think about it. And
I don't think
we
it's
have
that
to think
good.
that way.
Anyway, but it's not just the data that we're transmitting back and forth, right? We were having this whole conversation about ranging. I think it was actually in a meeting, not in a podcast. It gets blurry sometimes, but and I don't know which one of you wants to talk about ranging from the perspective of this whole pseudo-random bits that go out and come back, and like somehow we're able to figure it out from it. What is ranging?
I'll do it. I'll take a crack at it.
All right,
So
take a crack.
ranging there's a lot of different types of ranging that you can do, but at its core, ranging is a type of signal that you can send to some endpoint, and then depending on the response you get to that signal, you'll be able to somehow back out how long it took to get from the endpoint back to you. So for our instance, we're going, can I say this? We're going about 20 million kilometers away. I'm sure that's public information by now.
If it's not, it is now.
Oh,
I thought it was like 80 million kilometers.
No.
We've been definitely designing for 20.
Yeah, I was trying to
you
to eke out a response.
I was like, we.
I was
Well,
just
sorry
trying to
about
get a
that.
gut reaction there. Just
I
oh,
think
look
I
at that
probably
puck.
gave it
Well,
away
let's-
by 1 minute.
Hold
time
on, let's take a
flight.
step back before we go into this. When we talk about ranging, we're convoluting two things, which is, and they're referred to as pseudo range and pseudo range rate. Notice these from GPS because they're referred to as the same. So there is a way to get how far we are away from the Earth, and then a way to get how fast we are going relative to the Earth. And those are two different signals that come through. So
That's totally true, and we are using both.
Let's
I
take them.
believe
Let's take
we're-
them one at a time.
Sure. So for just the regular ranging, my understanding of the system we're using is that we'll be sending some cyclical code. This is not pseudo-random noise. We're sending some cyclical code that the satellite's going to spacecraft. I know that's a touchy subject.
it's not a satellite; it doesn't orbit the goddamn Earth,
I know.
Well,
The
it's
spacecraft
heliocentric.
receives. I
It's a
corrected
satellite
myself.
which is a spaceship. Sounds way fucking cooler.
Yeah,
I
fair.
could call it that.
Why can't we be like a minor planet?
We are going to be. I mean, that's what we're making.
Right. Okay.
Okay, continue on, Max.
All right, so our minor planet, it's going to receive
Yes.
this cyclical signal. This signal contains some subsignals that it's going to lock onto successively. When it's locked onto all X of those subsignals, it'll say, okay, I know what's going on. In our system, it's going to rebuild that signal, transmit it back. And then by the time we receive it on the ground, our ground decoder is going to lock onto each of those subsignals. And then through comparing what our ground station is currently transmitting to what it's currently receiving from the minor planet, it'll be able to take the difference between those two signals and say, okay, given that there was this much time between me sending this and me receiving something similar, this is how far away our satellite, I keep doing it, huh?
All right.
That's going to be out of my pay, I guess. Our spacecraft.
I'll
is.
explain this a little bit simpler. When we go to the moon, it takes 7 seconds to send a signal. When we go to Mars, it takes 15 minutes. We can use that as a way to get a sense of range, is how long it takes for a signal to go from Earth to the spacecraft and come back. It's really that simple. We're just counting the number of seconds.
Exactly. I was,
Times the speed of
maybe
light, you get a
over-explaining it
distance,
bit.
right? That's
But
really
that's
it.
exactly correct.
Well,
For
yeah,
do
sorry.
you want to go?
Oh no. Well, I just one thing, and I'm not a ranging expert by any stretch, but one thing that's interesting and kind of complicates it a little bit is like, what if your signal is very weak, right? So like you think that like at extreme distances, one of the tests we've been doing is we've been like trying to attenuate. So it's like he was saying before, like Max was saying before, reduce the power of the signal. We're trying to see like how weak of a signal can we still range with. And that depends on, and we'll talk all about it later, I'm sure, but like essentially how you're encoding your data. And so there is this other variable here of like, at the very edge, how far can we range out?
Yeah, but the core concept in physics remains the same, which is
Yeah.
we're sending something to the spacecraft and then sending back. And we do some processing on the radio actually to make sure that the loop back time is very consistent. And
Yeah.
you're correct that by staging those number of ones and zeros we send, we can help we essentially can increase the signal noise ratio and get a better turnaround. But at the end of the day, you're sending something at the speed of light and getting it back and counting that times distance or times seconds to get distance.
Exactly. The
Well-
other type of ranging, which is your range velocity, usually that's done through Doppler methods. So I'm sure that everyone at home has a good understanding of Doppler, but one classical example is...
I don't think it's velocity though. It gives us rate, right? Doppler cannot give you velocity. It's not
That is-
three-dimensional.
That is true.
He missed the
So-
word relative.
Yes, it is the change of distance between the ground station and the spacecraft along the path direction. So we can't tell, say, left and right velocity, but we can tell towards and away from velocity with respect to the ground station. And that is important because Doppler is not inconsistent, but it's hard to exactly back out what you're getting if you're moving tangentially to your line of sight. But in a nutshell, that Doppler shift will decrease the observed frequency of your signal if it's moving away from you, and increase the observed frequency of the signal if the source is moving towards you. So through some very fancy math, what we're going to do is send some tones up and down, and depending on what tones we receive versus what we know they should be, we can take that difference and say, okay, if the spacecraft, we know it's transmitting tones at this frequency, but we're receiving them at this frequency, then the spacecraft is moving away from us at a velocity of X to be able to generate those tones at the frequency we're seeing.
What kind of error rate do you have on that, right? Because you're going to send up a tone, right? So known frequency. Spacecraft is going to turn around at a known offset. You're going to get it back. You're going to measure it. Like, what's the? I mean, because light's fast, so the Doppler shift is going to be small. So what kind of error rate?
That's a great question, and I honestly cannot answer that.
Yes, love it when I get the host question that he can answer.
I think order of magnitude, and this might be total BS, but from what I can recall, I think we're looking at a frequency change of around 1 megahertz for 8 million kilometers per second away from us. Same thing towards us, but it's going to go in the opposite direction. So away from us lower, towards us higher by 1 million cycles per second. That's a megahertz.
Yeah.
The error bars on that, I cannot tell you. That's more of a GNC mission ops type
All right,
question.
Armand coming back again.
Yeah, James Bell is like the pro.
James
at
is the
this.
ranging goat.
Is he the guy that made the phone?
That's Alex. That's his brother.
That was
Alex.
his brother, Alex? Okay, cool. Alexander Graham Bell.
Oh,
Come
Jeez.
on, Robin. Jesus. Get on
sorry,
the
I
program.
didn't realize we were just going to dox all of our employees.
Oh well, sorry. James was on a podcast previously, right? I didn't mean to dox
He was.
James.
He
I like how Chris
Apologize.
is trying to be nice and
No,
like,
I was like,
appropriate.
oh
Chris,
no.
Chris Matt has put my phone number on this podcast.
Well, that's not. Anyway,
Yeah, that's
we
not
shouldn't
cool.
do more of that, right?
Yeah, no, we should not do more
we
of
should
that.
just title this Chris's phone number, see if he gets any calls.
Well,
let's not do that.
Since Chris is talking, you mentioned Chris earlier, like encoding. So talk to us more about encoding.
Oh yeah, and Max knows more about encoding than I do, but I think.
All right, never mind.
No,
Chris talked to me earlier today, and he had a really good way to kind of sum up what our coding is actually doing. So
Sure,
I'm gonna
maybe I
hand it
can
off
give
to
maybe
him.
like the smooth brain answer, which might be most helpful for people because like the encoding schemes, right? Like, what is the goal? The goal is I only have imagine a pipe, right? And I only have so many bits I can send down the pipe. Like we were talking about before, like when we're really far away. For our mission right now, we're sending 800 symbols per second, and we're using binary phase shift keying. So it essentially just means we get 800 bits per second of data we can send. You ideally want to get as much useful data as possible, right? And so let's say I'm sending like 101, right? Like that can be just like a number, right? So it could be a number in binary. That could be we have 3 switches and 2 are on and 1 is off. Like that's.
Hold on, let's back up a minute because you brought up modulation, and I'm not sure most of the people, all 3 people that listen to this, understand modulation.
Okay, I'm gonna defer to Max to explain modulation.
Let's talk about binary phase shift keying and what that means. What that means is pretty simple. If you think of a sine wave, it is inverting the phase of it. So when it goes up and down in a nice little smooth, flip it over, right? And we flip it, and every one of those transition points represents a change in that bit, going from a 0 to a 1. And that's all we do on this signal is keep flipping the signal to show it. Mm-hmm. That's how we do modulation of a signal. That's how we make ones and zeros. So once we have that, continue on, Chris. What do we do with it?
Yeah, and so if you're using BPSK, that means like your symbol rate, it's going to be 1-to-1 with your bit rate. And so once we do that, right, we have very little data we're sending. Like we were saying before, also with the latency, like ideally you want to get you want to. It's more valuable to be really sure that the data you're getting is correct. Because what you don't want to do, like you can also get errors, right? So you can think that you're getting, like you can get an output from your ground radio that's like 101, but how do you know that there wasn't some interference, there wasn't some problem that actually that's not what you got? Incorrect information, in my opinion, is like much worse than no information, right? Like you think the heaters are all on, but they're all off. And so there's a bunch of different ways that you can approach that problem. One thing that's very common on the internet and other things is you can just do what's like a standard error correction where you say, hey, there's some data where we can compute, like kind of similar to what we were talking about before with the file. I can run an algorithm on this data that will always produce like this value.
Like a very simple way to do it is just repeat the data twice. That's actually a very basic form of checking the data, right?
Right. And so you might ask, like, why not just repeat the data multiple times, right? So
why not just repeat the data multiple times?
This is what I was talking to Max about the other day, because it took me like 6 months to really understand this. I think at like a deeper level. But the reason is, if you think about it this way, let's say we're sending 101, right? And we can send that 3 times, and we can say if 2 out of 3 of any of those positions, so you do 101, 101, 101, let's say the first 2 are 1s, and then you get a 0. You're like, okay, well, majority wins, right? The first position is a 1. And so
data democracy, just take
data
a vote.
democracy. But now, for useful data, only 1/3 of all the bits you sent were bits that you really care about, like. And maybe it was worth it because you have more correct bits. But the thing with the codes that we're doing, and it's quite complicated exactly how the codes accomplish this, but the way I was thinking about it today is like, when I was talking to Max today, is like, you have 101, and now what you could do is just add more data. And this actually is very similar to how these things like the CRC and the hash work. You add more data, you can use it to check. But also what you can do is change the original data, so that the density of information that you can use to error check is actually higher. So you can change those bits and have an algorithm that you apply so that you can know what the correct bits must be. If you're only tolerant to a certain number of errors in the bits. But if you think about it, instead of assuming that the data has to be 101, can I transform it into a state where when I apply an algorithm, I can have high confidence like that's the correct 101. So now I'm using the data bits as part of the way that I correct errors, rather than just appending more information at the end.
So what happens if you only get half of that data packet?
Well, if there's a certain tolerance, and this is the truth of our system, right? Like if we only get 1 bit, right, like on deep space, like knock on wood, right, deep space 2, like we're not gonna know with our current scheme that we're using for coding. There's different ones. We're not gonna know whether that bit, if we just get 1 bit, is like actually a 1 or a 0. But if we get like 3 bits, then we'll be able to know. Like there's a point at which we start to get really, really big gains. Like I forget exactly how much, but order of like more than 6 dB, like we were talking about the decibels before, of gain, as though we had like a more powerful signal. And so it's really worth it to do these coding and to use that information as efficiently as possible. But it's not like there's no trade-off. Like there is a trade-off, and the different schemes have different trade-offs. There's different ways to do this.
Whew. All right. I think with that, I'm just going to move on to the mailbag.
Let's do it.
Let's do the mailbag.
Cool.
Wow.
Yeah, I don't.
I don't even know what just happened.
Yeah.
All that.
Lots of 1s and 0s and
Bummer.
fucking magic and something comes out. And Chris told me our packets don't work anymore. I'm confused.
And then we got back to DB.
Yeah. So.
All right, here we go. From Levi
Strauss?
Instead of high temperature magnets. Oh, this is from our solar panels with Wesley.
Oh, gosh, yeah.
Instead of high temperature magnets that are import controlled, why not use Velcro?
I don't know the answer to that, other than that's what? Use Velcro?
Yeah. I mean, actually, it's not a terrible idea, but okay, here's the deal. Velcro, you have to adhere it. So now you got to talk about the adhesive.
And it's got like a surface area and it's also very flexible, so that in Velcro would move.
Well, it would be a little
Wiggle.
but I bet it would. But it also has a more linear force range, right? So to break, so it would actually be more tolerant to small disturbances than like the magnet. It has a higher force, but once you're over the cliff, it's just going to flop around.
I don't know if that force is higher though to break it for magnet versus Velcro. I would assume it's actually higher than magnet. Like I felt those little magnets he has. They're strong.
Well, I'm going by like force per unit mass. I bet Velcro. I don't know. I bet
Don't we care
Velcro's
about
stronger,
on the
but
edge, though, it being force per unit area because you have a very thin area on the side. I mean, those panels are a 1/4 inch thick, right?
no, that's true.
It's not very big to glue onto.
Well, yeah, that's the problem. I actually am not worried about the Velcro so much as how do you get the Velcro to stay attached to the solar panel or the parent material. Like, I actually think that would be pretty hard. I mean, I guess you could like sew it on. Like you could put
Sew it onto carbon fiber.
Yeah, you use like metal wire and just
It's pretty amazing, actually. Just like
sew it.
saddle stitch it.
Yeah. All right. I actually think Velcro would be considered in the trade. I think magnets still win, but hey,
I don't know. We'll go ask Wesley and then
I don't
yell
know.
at him for not thinking
Good
about
suggestion, Levi. I like that one. All right. Anybody else that's got other BPSK suggestions for us, please?
it. Can we send Levi a shirt for giving us like a good question? I think it's the first good question we've ever gotten.
That's not true.
Send him one of the shitty shirts we got though.
What?
Yeah, I don't want to
You
give
mean
away
like the
good
ones
shirts.
that say Matt's are always right?
That's the company
That's
logo.
like a shittiest shirt. Okay, let's see what this one is. From Jonathan. Few know that JAXA used the solar sailing technique to save the Hayabusa 1 mission after they suffered a momentum dumping propellant leak. It worked so well that on Hayabusa 2, they used solar sailing to turn off 3 of their 4 reaction wheels to conserve power during their cruise phase. Have we also considered the solar sailing technique with our solar arrays?
Max?
Yeah, Max.
Max. I couldn't tell you.
Yeah.
No, I don't
That's
know.
that's a physics question. That should be Chris.
Chris?
I mean, I don't know. I think you'd need to ask, have we considered it?
It's not really, yeah,
know.
these aren't really RF or software kind of questions.
Yeah.
The answer is no. Moving on. From Jonas. How do you steer your spacecraft?
Oh, okay. Yeah, I can talk about that.
Yeah, hit it up.
There's a couple ways. So we've got reaction wheels. So those are wheels where we can spin them, and then you're going to get a corresponding spin of the spacecraft. We haven't seen exactly how ours are laid out for this mission, but usually you have them laid out like either.
We have a pyramid configuration, so we have 4. So that if any of them go dead, we have
Nice.
backups.
Cool. So we're like one fault.
Yeah,
tolerant.
and you really have to talk into the mic.
So there's whells that can help us turn around.
Unless you want the Doppler effect, like, just,
There's no.
Doppler.
There's wheels to help us turn, and then we also have like an electric propulsion system, and we have a gimbal on it. That actually, shout out Ravi Shah, one of our interns who wrote a lot of the code
Again
for the
with the
gimbal
last
system.
name, doxing.
I'm sorry. I think he'd be anyway.
Follow him on LinkedIn.
Apologies, I guess, Ravi. But he did great work where he wrote some of our controllers for the gimbal.
I'm trying to decide, is Christopher the nice guy or the doxer?
I think he's one of these guys that comes off as really nice, but then you like analyze what he says, and you're like, wow, that guy's kind of an asshole. I like it. I like it, Chris.
Okay, I guess. I'm just trying to think like, yeah, sorry. Shout out to people. But anyway, one of our interns actually wrote a lot of the code for this. But it's really cool where we have a gimbal, we have an electric propulsion system, which doesn't have a lot of force, but over long periods of time we can go pretty fast, and then we can turn where that's thrusting. And so the combo of those two, and then we have some star trackers so we know which direction we're pointing. We can continue pointing in the right. We can steer in the right direction.
Yeah, we don't like. Let's talk about steering for a second. When we talk about it that way, we don't steer a car. It's not like you fly an airplane like it is in Star Wars.
No, we
right?
said we have
There's-
wheels, like steering wheels.
Yeah,
Reaction.
they don't work
wheels,
that way. We can spin and roll, pitch, and yaw in 3 axes, and then we can translate that with our thruster in any
We
direction.
control our
So
attitude.
our attitude, right? A pull, and then the way we go a different velocity or position direction is by turning our thruster and firing the thruster. So it's a very different way to think about steering a spacecraft.
Yep.
Or than steering a car.
All right. Well, this is the portion of the episode where our guests actually get to ask Matt a question.
Damn, Robin's the host, so he gets to dox me on this.
I get to make the rules. All right. Who wants to go first?
How deep are we going for Deep Space 3? What's going to be my path range there?
The same distance. There's no reason to go farther. There's
Okay.
a lot of targets we have within the round, within the bounds of what we've set up. So what does it come down to? It comes to operating within that bounds. We're not in the business of seeing how far we can go away from the planet. That doesn't make a better business model, right? We're not trying to beat Voyager. We're trying to make sure we have accessible asteroids that we can go after for the minerals we care about within that box. And the box we've defined, we think, contains enough to do it. In fact, through about the next 7 years of launch windows right now is what we've looked at, and we have enough targets to go after. So maybe in 7 years we'll go farther.
Okay, so follow up to that.
I mean, unless somebody wants to pay us to go on a different mission.
Even then, as long as it corresponds with what we're doing and buys down risk on our
has to be
missions,
what we're
great.
doing,
but yeah, it's got
If
to be.
somebody
It's
wants
got
to
to be
go
relevant.
deeper.
Follow up to that. Do we know what can we talk about what asteroid we're going to for Deep Space 2? Do we know yet?
So here's the honest truth. We don't know, right? We have a
Okay,
target
so-
selection group of what is, as of today, is 19 asteroids on launch day that we can choose from, and we'll continue to get more data on them to see which one is right. I have a couple favorites. I have one that I really, really love, and I hope it comes within our launch window, right? It's probably one of the most lucrative ones out there. And if we do end up going to that one, we will tell nobody. If we go to a shitty one, I'll let you know.
And just
No, you asked your question. You only get one.
Yeah, it's one question. It was a
That's a
follow-up.
bummer, huh? All right, go ahead. One more.
well, just when you say your favorite one, is that like spectroscopy or just albedo, or like how do you know that it's like a particularly lucrative
So
one?
that one specifically, we have lots of images taken of it. We also have some spectroscopy data on it.
Sweet.
So we have a lot of correlation to say that we believe it's highly metallic asteroid.
Nice.
And it's also right within the right size range, in the right spin range, accessible, the right number of times. Right, it kind of like fits all those criteria we have listed out very, very well. So that's why we love it.
Sweet.
All right. Well, there you go. I think that's a wrap for today. And next time, hopefully, we have Chap instead of him just being lazy.
Yeah, by the way, Chap is here in the office. He's just upstairs.
Yeah, he totally walked into the room and was like, "Oh, there's not enough chairs," and walked out. I didn't realize we had a one guest limit.
Also, I was specifically late, so I could be the one that walked in and said there's not enough chairs and walked out. So what the fuck?
I got
right.
places to go. All right, we're out. Thanks,
Laters.
everyone.